Right. Let's get started. Welcome everyone to the Simons Institute and this workshop. My name is Venkat Guruswamy and I'm a senior scientist here at the Simons Institute for the Theory of Computing. And it's my great pleasure to welcome you to the Institute and this week's workshop. As all of you, I'm sure know, the Simons Institute is the leading international venue for collaborative research on theoretical computer science. It was established in 2012 with a generous grant from the Simons Foundation, which continues to support us very generously now. And the Institute brings together the world's leading researchers in the theory of computing and related fields, as well as the next generation of outstanding young scholars. This is the 10th year of programs at the Simons Institute, and we are really proud as a community of the achievements of the wide-ranging programs which have pushed the frontiers of TCS in many directions, making progress on long-standing challenges of the field, as well as opening up new directions of inquiry. So each semester, the Simons Institute hosts two central programs that attract several long-term visitors, junior and senior to Berkeley. And the programs also include multiple workshops that convene more short-term visitors. So this semester, we have an extended reunion of the Satisfiability program, which happened a couple of years ago, alongside a full program on meta-complexity. And there's a lot of synergy and connections between these programs and topics, which is very exciting to see every day here. And today I would like to welcome you to the workshop associated with the reunion on satisfiability. And the workshop is titled Satisfiability, Theory, Practice, and Beyond. First, I would like to thank the organizers of the workshop for their work putting together an outstanding program. And just to acknowledge the organizers, they are Jakob Nordstrom, who's here and to whom I'll pass the mic shortly to say more interesting stuff about the workshop, and Claren McCreish, Kuldeep Singh Meal, and Martina Seidel. Thanks again for organizing. And I would like to just go over a few logistics for the coming week. Food is provided outside before the first talk, and food and coffee is provided outside before the first talk and during the breaks. And for lunch, you're on your own, but there are many excellent choices to go within short walking distance. And we ask that you please leave any food and drinks outside the auditorium so that we can keep the auditorium clean and nice to use. And if you need to store your stuff for going out for lunch or otherwise, there are lockers in the other side, far side of the building, which you can use. And our videographer, Omir Far, will be here to help with any AV and other issues throughout the day. And I'm not sure, is this a hybrid workshop or no?
It might be, I'm not sure.
Okay, so okay, I'll skip that point then. But if it is a hybrid workshop, there will be somebody monitoring and you can ask questions remotely, and of course in person here. And finally, last but not least, I would like to give a special thanks to the events team who put all this thing together. So that's Ashley Hassan and Elizabeth Yuan for managing all the logistics of not only what's happening this week here, but also arrangements to accommodate our short-term visitors who are visiting for the week. Okay, so thanks, Ashley and Elizabeth. So with that, I'll hand it over to Jakob to introduce the workshop. Thanks and welcome everyone.
Thanks a lot, Venkat. So I just want to start by saying that it's great to see all of you here. Finally, as you know, we tried to run this program in 2021, but there was a pandemic who meant otherwise. And so now we're very grateful to the Simons Institute for getting the chance to run this extended reunion, at least the sort of half of a program. This is fantastic. And this is what is intended to be like the main workshop of this Satisfiability, Theory, Practice, and Beyond program. And we hope the intention is that we really want to collect both theoretical and practical research related to satisfiability and combinatorial problems more in general. And so what we're hoping for, I think, if you look back at the original program in 2021 was meant to celebrate 50 years of NP completeness. And I think NP has had a pretty good run if you look back on the last 50 years. And so one way of viewing this workshop as we're gathering here is to talk about, look back at some of the research that has been done, but also plan for the next 50 years. You know, what are we going to do next? And in particular, we're hoping for during the talks to see a lot of focus on open problems, on exciting new research directions, and also to discuss possible connections between theory and practice. One of the, I think, main reasons behind this program in the first place is that different communities have such a different view of SAT and other NP complete problems. For at least, for me as a theoretician, the way I was taught to think about NP, it was like super scary. It's it's a dead end. Don't go there. There's nothing we can do. And it was really like a shock and a very disturbing experience for me to meet practitioners who were thinking about NP as, if they could finally get it to NP, then they were done. That's when they started writing their papers, because they knew how to solve NP complete problems efficiently, which I was convinced was exponentially hard. Of course, this is simplifying a little bit, but still, it is true that there's like a very different views of these NP complete problems, NP hard problems, and beyond on them. From a theoretical point of view, we do believe that they're very, very hard, at least in the worst case, but we don't know how to prove that. I mean, that's one of the big open millennium problems. On the practical side, there are amazing algorithms. We'll hear it during this week for Boolean satisfiability, even for optimization problems such as MaxSat, constraint programming, mixed interlinear programming. But I think it's fair to say we don't really have a good scientific understanding of how these algorithms can be so unreasonably good. And so these are some of the problems that we'll be hoping to talk about from different angles and discuss. And not only during the presentations, we're hoping for lots and lots of questions, and of course discussions during lunch breaks, during coffee breaks, etc. So the plan of the program is basically that for the first 2 days, we're mixing sort of theory and practice of Boolean satisfiability in a more strict sense, talking about with a focus on proof complexity and computational complexity theory on one hand, and on satisfiability solving. That's Monday, Tuesday. On Wednesday, we're moving on to things like constraint programming, operations research, algebraic approaches. Thursday has more of a focus on how we can leverage research on these types of problems for questions like formal verification, verified computing. And then Friday is kind of the beyond day, where we pick up a lot of different topics that are inspired by, but not strictly related to that. So again, it's great to see so many of you here. And I think we can maybe even get started with our first talks. Our opening speaker is Atserias from UPC Barcelona, who will tell us where the hard problems are, or maybe at least about how he searches for them. So Albert, without further ado, please, the floor is yours.
Thank you very much. Okay, thank you very much for the introduction. Actually, I was thinking we started at fast, right? So I'll start slowly, just in case someone wants to come in. All right, so yeah, I want to talk about the search of hard instances. Now, that's not searching for them in any sense of computational sense, but rather in a mathematical sense. So we want to understand what are the hard instances for algorithms. And the question is, why do you want to do that? Well, my claim is that, in fact, this is the only way, or basically the way to evaluate your algorithms and then try to improve them. If you don't know where your algorithms fail, then it's very hard to know what you need to enhance your algorithm with to improve it. Right? Well, as many of you told me these recent days, and Jakob mentioned it now, the 2021 program was meant to celebrate 50 years of satisfiability of NP completeness, as Jakob said. And this is 50 years of the paper by Steve Cook, which appeared in Stock in 1971. And there he proved that SAT is NP complete, but his interest, as you can see from the title, was on analyzing the complexity of theorem-proven procedures. Okay, so the very first few sentences of the summary, it is shown that any recognition problem solved by a polynomial time-bounded non-deterministic machine can be reduced to the problem of determining whether a given propositional formula is a tautology. And of course, the negation of a tautology is a satisfiable instance. Satisfiability problem is the complementary problem of the tautology problem. And there is a passage in the paper that is particularly important, and especially this last sentence. And so let me read it to you. So he says in the middle of the paper, he says that the field of mechanical theorem proving badly needs a basis for comparing and evaluating the dozens of procedures which appear in the literature. Already then there was a bit of a mess, and it was not clear which techniques were useful and which were not useful. And Cook was asking for analyzing this and making a theory out of it. He makes commentary about examples by computer is a good criterion. So the performance is a good criterion, but it's not sufficient. And then he goes ahead and says that the theoretical complexity criterion is needed, which will bring out fundamental limitations and suggest new goals to pursue. So in fact, this very last sentence, to suggest new goals to pursue, is what I want to emphasize in this talk. I have to say that this sentence actually falls in the second column of the paper. So I took it down here, and in previous talk that I gave, I had cut it down here. So bring out fundamental limitations. I had completed the word myself. But I think the sentence that follows it is actually quite important, because when you find the hard instances, this is the fundamental limitations, then you have new goals to pursue, which is solve those hard instances. So here's a complexity theory's dream. Right? Or proof complexity theory's dream. You have this CNF formula in Dimax format, as you can see, and you want to tell, it would be ideal if you could tell, oh, I see this, yeah, sure, this takes 7,904 clauses to refute in resolution. That would be ideal, right? That's the final goal. We would be able to understand sentences or CNF formulas at this level, but this is just hopeless. And now we know why it's hopeless. We have specific results that explain why it is hard to find the size of the shortest resolution refutation. This was not clear before, and there are many cases where you can find actually very short resolution refutations when they exist, but in general, this is a hard problem. Still, we did quite a lot of progress in proof complexity, trying to delineate which CNF formulas are hard and which are easy. So let me introduce now a little selection. This is an opening talk, so I'll stay at a high level. So I'll explain a little bit a selection of themes in proof complexity, 3 themes, and then I'll go deeper into one of them. So here are 3 themes, and these are by no means the only things that have been done in proof complexity. So the first theme is the theme of lower bounds and upper bounds, and I want to emphasize the upper bound part, because lower bound is what usually we stands out as most difficult in proof complexity, but the upper bound part is good and necessary for the program that I'm putting forward. So here is an example. This is actually a theorem of Haken, which says that every resolution refutation of the pigeonhole principal formulas, PHPN, must be of exponential size. This is a lower bound result. This was proved by Haken in 1986. This is 15 years after Cook's paper, and it actually answers a question in Cook's paper, which is give lower bounds to the DPLL procedure. This was known before, but Haken gives stronger lower bounds to the DPLL procedure, actually applying to general resolution, as we'll see in a second. Now, this is not only useful as answering that question and as identifying one hard instance, but this hard instance is actually quite common, and it appears in many contexts. But for example, it is used to provide lower bounds in the black box model of the black box query model for total functions in NP classes, the TFNP classes. So this has been used when we want to show that several problems of total functions in NP are incomparable one to the other. Then the kind of techniques that are used to prove lower bounds for the pigeonhole principle are used to separate the classes. This has been quite insightful for people in economics and in other areas. All right, so this is one instance of this thing. Now, the other important aspect of this is that this lower bound is actually tight, and we're after tight bounds. So we want tight up to the constant in the exponent, so up to a polynomial factor. It's tight because you have also an upper bound of 2 to the O of n, but it's also insightful because in fact we can see that this upper bound cannot be tree-like. So the resolution refutation cannot be tree-like because the tree-like resolution refutation The smallest is bigger than this. It's more of the type n factorial, like 2 to the n times log. So this sort of tight upper bounds will also appear later in the talk. And this is one of the first themes. So I'm going to emphasize 3 themes. The one is lower bounds and upper bounds, and this is the first. Another theme that proof complexity theorists have been looking at is that of proof search or automatability. Here, the problem is that you're given an unsatisfiable formula, and the question is, you want to find a resolution refutation. And I'm focusing on resolution for now. Later, we'll talk about other proof systems. Or at least you want to estimate the resolution proof length of F. And remember, this was the dream of the proof complexity theorist, is you're given the CNF. Can you estimate the proof size before you even start running your solver? If the proof size is too big, then you might as well do something else because it would take too long if you're generating resolution proofs. So it turns out that this problem is very hard. And now we know this. Now we know that it's both problems, or both instances of the same problem are NP hard to solve, even very approximately, in a way that matches algorithms that are sub-exponential for the same problem. This was proved only recently, a few years ago, a couple of years before 2021, when the program started. There were some evidence that the problem was hard, but it didn't reach the point of NP hardness until 2019. So automatability is, of course, an important question, and this is another theme that proof complexity theorists have been looking at. Now, the third theme that I'm emphasizing is the application to analysis of heuristics. And this is an extremely important area, and this is only one attempt to contribute to this area of how do you analyze heuristics. The algorithms that are written in practice are not always not always proof guarantees for them, polynomial time guarantees or linear time guarantees or anything like this. So you need to rely on heuristics, especially if your problem is NP hard, as the problem of finding refutations, for example. Now we know. So how do you analyze the heuristics? Which ones are better than others, and how do you classify them? And again, here, identifying the hard instances for the heuristics is one step forward, I claim, towards trying to do this. So 3 ways you can analyze heuristics, for example, through average case complexity. And that has interest, it's interesting in its own right, like the Erdos-Renyi random graph model or the random model of 3 CNF formulas. And these are interesting for special by themselves. And we'll get to them. Actually, we'll talk a lot about Erdos-Renyi. In fact, approximation algorithms are also an area where the analysis of heuristics is important, because after all, an approximation algorithm is a heuristic. It's trying to solve the problem exactly, and the only thing it does is that it finds an approximation. And then, of course, you want to prove some guarantees of this approximation. And then what proof complexity can offer here is hard instances, in the sense that gap instances. So instances where the algorithm claims some value, and then you show that this value is far from the actual optimal. You're thinking of optimization problems. And then finally, the analysis of heuristics for branching and searching within search spaces this is, of course, what we know in what we do in Satisfiability. So these are the 3 themes that I wanted to emphasize. And I said I will focus on resolution because, well, first day of the workshop, we want to talk about Boolean satisfiability, but I'm going to be comparing the proof system and satisfiability with other proof systems. So, but the language, I want to keep it to the language of satisfiability, clauses that are very simple, and because the satisfiability problem is the one that we understand better from the point of view of explicitity. In fact, Cook proved that SAT is NP complete, but it was in the air the concept of completeness at the time in 1971. So in fact, people working in integer linear programming, they were also doing reductions between problems, and they were expressing their problems as integer linear programs or 0-1 linear programs. And it could have happened that someone else proved that 0-1 integer linear programming is NP complete in the same way that Cook did. And then the history would have been quite different, I believe, right? So Cook put the emphasis in the logic by proving that SAT is NP complete. But if 0-1 integer linear programming had been proved NP-complete first, maybe the theory would have deviated towards 0-1 integer linear programming as a framework on which to express the problems. Of course, that's still a framework where things are done. But here we want to focus on the satisfiability on the language of logic. For resolution inference rule, given two clauses with a clashing literal, you can resolve the literal out. And inference-based proofs are what you can see here. It's a sequence of proofs, one after another. And you have a left premise and a right premise of the resolution rule. So this is the resolvent of these two clauses. And each one is either the resolvent of two previous clauses or one hypothesis from your original form. And now we measure the proof size. And we have two flavors of size. We can measure the size as just the length as it is here. And this is what we call DAG size, because we're imagining this sequence as a graph, the graph given by the edges, the back edges, pointing to the previous hypothesis. You could also imagine this as requiring this to be a tree, and then you would measure this as a tree size. So the size of the proof is the size of the smallest of the tree. And then the tree size of a refutation of the tree size complexity of a formula would be the size of the smallest tree. And there are two other important measures, width and space, width particularly because there are tight connections and interesting connections between size and width. These are the Benson-Peterson relationships. I'm sure this will appear later in the workshop also. So as I said, I want to focus on satisfiability, but I want to also introduce the concept of algebraic proofs because somehow I want to compare and I want to find hard instances for resolution that happen to be easy for other kinds of proofs, because that's what I want to do. I want to do progress, remember. I want to identify the hard instances to know what do we need to shoot for. So let me introduce algebraic proofs and then we'll get to that. So algebraic proofs are proofs where now the variables, you can think of them now as ranging over some ring, because you're going to be talking about the ring of polynomials. Rather than variables, these are now indeterminates. And then you impose the Boolean axiom saying that, well, after all, they are in the ring, but they are 0 or 1. So that's the Boolean axiom. You impose this, and then you impose that they are complementary x and xi prime. Introduce one variable for the negation for each original one. And then clauses become polynomial equations, like if at least one of these must be true, then this means that at least one of these must be 0. Right? Have clauses represented as polynomial equations. And then the inferences, like the resolution rule, or any other inference you can imagine, become polynomial identities. From a bunch of polynomials, you can compose them in some way and get another polynomial equation. If these equations are satisfied, then by applying the identity, you get another equation is satisfied. And that one you can add to your reasoning. How is this identity actually is what I call sum of monomials proofs or sums of squares proofs. This sums of squares is a pretty standard term by now. Sums of monomials is not so standard. It's what people call Sherali-Adams proofs. Sherali and Adams. So I'm going to call them sums of monomials because basically what you're doing is the following here. So you're having an identity, a polynomial identity, and this identity is supposed to be a proof that your formula F, the equations that represent the clauses of your formula, entail that P is non-negative. P is non-negative on all the Boolean assignments because the axioms of the Boolean assignments are always present. How are they present? Well, because the identity uses these AIs are clauses of F or clauses that come from the Boolean axioms. So these are your hypotheses. And those ones you can lift by an arbitrary polynomial. The reason being that these equations are actually equalities. These are equations. So if this is 0, then whatever you multiply by, it's still 0. And then you add, you can add, depending on which proof system you are in, you can add either polynomials, which are just products of variables, and those are non-negative by default. And on top of it, you're adding a non-negative coefficient in front, or you can add sums of squares of other polynomials, and those are non-negative because we are in the reals. By the way, I didn't say that, but this works over the reals. Okay, so squares of polynomials over the reals are always non-negative. Therefore, if you compose them with positive coefficients, then what you get in the end is something that is guaranteed to be non-negative. All right, so this is your inference, and resolution can be put as an example of this inference rule. And so now we're going to say that you have, for example, a contradiction. How do you prove a contradiction? How do you prove that something is unsatisfiable? Well, you derive -1. So you have an identity with the original axioms from the formula. You add some stuff to it, and the cancellations cause here -1. So this identity give you -1 is a refutation of f. And we can measure the size and the degree and the bit size, and these are the different types of measures of a proof. For example, degree will measure the degree of all the components that you see here. And it's important that we're measuring the degree of the components because the degree of everything could be much smaller. Like, for example, the -1 case, right? You want to say, and you measure the degree of the components that you're using, the lifts and the squares or the monomials that you're using. Monomial size would count how many monomials you have in total, and that's the measure of the representation of this polynomial as an explicit sum of monomials. And the bit size is also an important one because these coefficients in some instances might be completely huge, and that would make the proof infeasible. All right, so these are this is the algebraic proof systems that I want to focus on. Now, the lovers of polynomial calculus will say, well, there is also this polynomial calculus proof system. I'm not talking about it here, but it also fits quite nicely, especially in this slide. So here you're working on an arbitrary field or ring, and then the polynomial calculus derives new equations from all. And while these proof systems are thought as one identity, so you have one identity, and the size is just how many monomials you have in total. You could also iterate this, but we're not going to do it now today. What's the point of sum of monomials and sum of squares proofs? Well, there are 2 points. One point is that it adds the power of counting to the language of propositional logic. So of course, we're increasing the language for reasoning. The specification of the problem is still clauses. That's how I want to look at it. I don't want to look at for now as at optimization problems. I want to look at satisfiability or decision problems. So, but the reasoning language should be a bit stronger. So, for example, now from the clauses of the pigeonhole principle, which I didn't introduce, but I'm sure many of you know, you can derive anything. It's unsatisfiable, but in particular, you can derive this that says that at most one pigeon sits in hole H. And you can think of these variables as saying that pigeon I sits in hole H. And now, if you look at this inequality, it says that the sum of the pigeons that go to H, the sum is over I, is at most 1. So there is at most 1 pigeon sitting in hole H. So here is the short SOS proof. This is what we want to derive. This is non-negative. Why is it non-negative? Well, because it's the sum of a square. Here it is. It doesn't matter which one. It's a square plus Boolean axioms. In this case, multiplied by -1. Why not? After all, this is supposed to be 0. And the whole exclusivity axioms, which come from the PHP formula. So these axioms say that you don't have 2 pigeons, different ones, sitting on the same hole. These are basic axioms from the specification. You can also leave them by -1. They are supposed to be 0. And if you do this identity, you open up the parentheses, you get this thing. And now, once you have this, now you can imagine that by adding all the proofs for the different holes, you will get that the number of pigeons flying is at most n. But on the other hand, we also know from PHP that the number of pigeons flying is at least n plus 1. So you get the contradiction, -1 is bigger. Well, in other words, the pigeonhole principle has a very short and small degree 2 refutation in sum of squares proofs. So that's a powerful thing. What about sum of monomials? Well, in that case, the degree is not small for the pigeonhole, but you can at least show that the monomial size is small. So there is a monomial size proof. So this language gives you more power. That's one of the points. And again, it's language for reasoning, not for specification of the process. Now, another reason is that this area of sum of squares proofs and it's classics of combinatorics and of definite programming, which are very well studied in the mathematical community and have very deep theory that we could try to exploit. So, for example, it meets this classic of semi-definite programming, SDP, which is the Lovász theta function, and this is the definition. So the Lovász theta has several alternative definitions, and this is the theta 3. I strongly recommend, I see Don Muth in the audience, he has a very nice paper called the sandwich theorem, which summarizes the various definitions of the Lovász theta and how they are equivalent. And, so the Lovász theta is based on the concept of orthogonal representations. So you have this graph, let's say the pentagon, you have 5 edges, and you want to represent it geometrically somehow. And the way you do it is you take, for every vertex, you assign a unit vector. And then what you want to find is a configuration of these unit vectors in such a way that non-edges get orthogonal vectors. So this means you need to go to pretty high dimension to be able to do that, but in principle, it's always possible by taking large enough dimension. In principle, it's always possible. So you go to high dimension and represent your vertices as vectors that are orthogonal on non-edges. And then you want to optimize some kind of a function subject to some normalization constraint. And that's the function that you want to optimize is the one for the Lovász theta. Okay, this function, is it arbitrary? Well, no, it's meant to capture the purpose of the Lovász theta, which is the one captured by the sandwich theorem. So the sandwich theorem says that if you take the theta of the complement of the graph, this is going to be sandwiched between the clique number of G, which is the largest complete subgraph you can find in G, and the chromatic number of G, which is the smallest number of colors with which you can color the vertices so that there is no monochromatic edge. So in some sense, this is then giving a sandwich or an interpolant between these two very hard to compute quantities of a graph. While the point is that this is computable by semi-definite programming and therefore polynomial time solvable. And there are solvers for semi-definite programming, you can hope to use them. Now, how does this connect to sum of squares proofs? Well, it is observed in this paper, Banks, Clymer, and Moore, they do a lot more. They analyze actually the value of the Lovász theta on random graphs, and we'll get to those in a second. But one thing the way they motivate the study is also by showing that, in fact, the Lovász theta being bigger than Q, what does it mean? Well, it means that the chromatic number is bigger than Q. So it gives a lower bound on the chromatic number. That's quite hard because this is a minimization parameter. So saying that it's bigger than Q, it means that there is no coloring with Q colors, right? So you're ruling out an exponential set of things. So this corresponds exactly to having degree 2 refutation of the CNF formula. They don't write it as CNF, but you see their equations, and they are basically the CNF formula that says that the graph G is Q colorable. This is basically the standard CNF encoding. So in fact, their encoding of colorability is basically the polynomial translation of the CNF encoding, the standard one. Which one is it? I'll get to that in a second. Good. So there are these two good reasons or interesting reasons to focus on algebraic proofs. One is that they add expressive power to the reasoning. And second, they connect to very well studied areas in mathematics and combinatorics. So now let me focus, because these two appeared already in the sandwich theorem. So let me focus in this analysis of heuristics and how we actually connect to sum of squares proofs. So we want to analyze the CNF encodings of the problem whether G has a K-clique, and the CNF encoding of whether G is Q colorable. Let's see what we can say about this. And this has been studied for many years. Steady progress. And again, the hope is that from this analysis, extract new ideas for progress, like Cook wanted in his 1971 paper. Let's start with the clique problem. Given a graph and an integer, does it have a K-clique? A complete subgraph of size K. Very well studied problem in computational complexity. I'm not going to read all this. It's NP complete. Karp in 1972 proved it. And then there's a long series of things. To emphasize that Karp himself observed that this appears to be hard on average for random graphs. It's hard to approximate. There are secret complexity lower bounds, etc., etc.
Sorry, just out of curiosity, is a Karp's claim, was that like an empirical claim or was it like a theoretical claim? Did he actually run experiments, or he was like speculating for other reasons?
He was writing programs to solve things. Yeah, just read that. But still, he was interested in average case analysis of algorithms. And this is a very interesting test case, because if it's hard, well, I think the most interesting outcome for him would have been to find that it is easy. That we find some structure that makes a clique solvable here. But we'll get to that in a second. All right, so let me start with this. Here's a common heuristic that is used by practical clique solvers, as I'm told. You want to know whether a graph has a K-clique or not. Then what you start doing is you greedily color properly, in the sense that without monochromatic edges, the vertices with as few colors as you can. And if this happens to be K-1, then you already know there is no K-clique. K-clique is not K-1. But of course, usually you get something like 5K or I don't know, 100 colors or some big number. And now the point is that now you can branch on different color classes, because you know that, well, if these are color classes, then these are independent sets, so there are no edges here. So if there is a clique, it's going to have one vertex in a different color class, right? And then you do some kind of backtracking, like branch and bound. When the current clique size that you have at this moment plus the number of remaining colors is strictly smaller than K, then you know you cannot complete that branch, so you backtrack. Okay, and of course, many more complex heuristics are certainly possible. Like instead of coloring with that, you could color with the lowest theta. There are several heuristics you can imagine, but these are not analyzed so far, as I know. Probably because it's too hard to compute this, or maybe because we don't know what to do out of it, but we'll see. How is the things encoded? Well, you have a propositional variable says that U is the ith vertex of the clique, and then you have clauses saying that for every I, there is one element that is the ith element of the clique, and then for every non-edge, you forbid that I is U and J is V, because it's a non-edge. This is the standard encoding of the formula. And the resolution proof complexity has been studied, but it's not settled, surprisingly. But first, there is this obvious observation that if you do the exhaustive enumeration of K element subsets, then of course you can refute the formula in size at most n to the K. That's not very insightful, because that's exhaustive search after all. So in this setting, the target size that we should improve is this n to the K. This is true even for 3-layer resolution. And then Olaf, Nicola, and Massimo asked in 2013, they asked whether you can prove lower bounds of this type, n to the omega K, for general resolution. And the motivation for this is that it turns out that they observed that the resolution can simulate many of the practical algorithms and heuristics. But also importantly for this target of understanding the hard instances is that this seems to require new techniques, because the methods that we had for proving lower bounds, like for the pigeonhole principle, they don't apply, they don't work. And this turned out to be a very interesting question, and there's been some progress. So themselves, in the same paper, they gave a lower bound. They said, well, for 3-leg resolution, at least, they can show n to the omega k lower bound. Moreover, it's not only a worst case lower bound that you can find. This means that you can find a graph or a sequence of graphs for which this happens, but they show that it's actually on average exactly at the threshold, or barely at the threshold where cliques start not appearing after this, and then the formula is actually hard. By the way, if the clique appears, then the formula is impossible to refute, right? Because it's satisfiable. So the interesting case is when there are no cliques in the graph, and in that case, it's still hard to refute. Now, is this a good thing? Well, yes, because now at least you know this is a generator of hard instances. So it's hard instances for 3-leg resolution. So if you want to, if your solver is basically only DPLL, it's only 3-leg resolution, then this is a test set of very wide class of test cases where you can try to improve your solver and test it. So, but of course, the question we as theorists we ask is, what is it from the random graph that is really needed to use the hard instances? Because this way we can extract the difficulty and focus on that and try to improve your algorithms by trying to find or avoid that difficulty. So here is the structure of lower bounds proofs that work for random instances. Typical. I mean, not always like this, but this is the way that it's done in this case. You first identify a property of the graph, and if the graph has this certain property, then you show that the formula is hard. It's a lower bound. If G has the property, then the 3-leg resolution complexity is n to the omega k. And now you prove that with high probability, a random graph has this property almost asymptotically, almost surely. And the property in this case, there are several you can come out with, but this is one that actually appeared in other contexts, like in the context in asymptotic combinatorics. So this is called the rich extension property, which says that if you look at any constant fraction subset of vertices in the graph in G and P, with this P, then it has many common neighbors. I mean, many means almost, I mean, sublinear fraction, but many. So this is called the extension property when you have one common neighbor, and the rich extension property means that you have several, many. And the complete, so the problem with this property is that, well, nice, it fits this, therefore it becomes hard for 3-leg resolution, but it has it. But it turns out that this is satisfied also for easy instances. So if you look at the complete k-1 partite graph, I denote it like this. So these are k-1 classes where you have all edges between different classes. Now this is of course doesn't have a k-clique, it's a no instance. But it turns out that 3-leg resolution does not know how to refute the k-clique, even though it's obviously doesn't have a k-clique, and we know very easily why. It doesn't refute it. Yes.
K and k-1, call it a k-1.
Yeah, okay, I'll explain. So here you have k-1 parts. The vertices, the n vertices are divided into k-1 parts of equal size, and then you put edges between different parts. This is a complete k-1 partite graph. All right, so it turns out that the rich extension property is satisfied in this graph. Therefore, this graph is hard for 3-leg resolution. So this property is not good enough to. It will not be good enough because it turns out that on k-1 colorable graphs, these are not hard instances for general resolution. Yes.
Asymptotically, Is it asymptotic? Fix K and then goes to infinity or,
Yes, imagine K is much more than N. Yes.
okay,
And go with K up to log N.
and the K is going to infinity too. I don't see how this is going to help me when K equals 10, for example.
Well, complete graphs with 10 or 15 vertices are quite different.
If K is 10, K over C, I mean, there are asymptotics going on, but I'm not sure exactly
Okay.
how things are going to infinity.
Yeah, you can actually think of K growing to infinity, but it has to grow quite slow for this to make sense. Like K over something like log N.
Okay, yeah.
But it is one way of answering this question is saying like you could imagine like, you know, can resolution refute the K-clique maybe in some const like cubic time or n to the 4 or n to the 5, and I guess this is sort of asking if you have an n to the omega of k lower bound, then you're saying no, that's not the case. Like there is, like as you fix your K-clique to be some sufficiently large constant, then you won't be able to refute clique formulas for that constant in, say, whatever cubic or n to the 4 or n to the 5. I don't know if that's related to your question.
Yeah, this is what I have in mind. So you have a fixed K but large K, and then n goes to infinity. And then we want to compare against n squared algorithms or n cube algorithms. So, like in the parameterized complexity setting, where we want to focus for algorithms that are of the type fixed polynomial in n, so n squared times maybe a function that grows with k badly, maybe exponential in k. In fact, this will appear now in a second. It appears here. So if I may continue, now it turns out that the k-1 colorable graphs are not hard instances for resolution. They are hard for tree-like resolution because they satisfy this extension property, but they are not hard for resolution. And this was observed in the original paper, in that if a graph is k-1 colorable, in particular the complete graph, the complete k-1 parted graph, then its resolution complexity is polynomial or fixed polynomial independent of k, while sure exponential in k. And the reason this happens is that, well, there is a pigeonhole instance inside. So you have only k-1 colors. And these k-1 colors, you want to fit a clique of size, so let's say classes are 4, you want to fit a 5 clique, and then you're going to have 2 vertices sitting in the same color class. And this you can imagine as an instance of k pigeons and k-1 meta holes. So the meta hole is the independent task. Now it's interesting to compare this with the Lovaas-Theta sandwich theorem, because that also provides a certificate of not having a k-clique, because if the chromatic number is k-1, the Lovaas-Theta function is also at most k-1, and therefore that's an upper bound on the clique number. But this is not polynomial in both n and k as the Lovaas-Theta would be, but at least it depends nicely on k. So the k doesn't appear in the exponent. And in some sense, this is a better, more structure, or at least it remains to be seen how these things compare. So the certificate provided by the Lovaas-Theta, remember, sum of squares proof. What is it? What is the certificate of the sum of squares proof in this case? Is it a pigeonhole instance? We already saw that pigeonhole is refutable in degree 2, but I haven't seen this explicitly with my eyes. In particular, in particular for the random graph. We'll get to that again. All right, so now there is, let's go beyond resolution, tree-like resolution. We said the k-1 parted instances are easy for resolution. So what can we find as hard for the resolution? It turns out that we can prove lower bounds for regular resolution, but now it has to be for the random graph. The k-1 parted graph doesn't work. In fact, the question, again, we ask is what from the random graph we use to produce the hard instances. And in this case, the property is not this k-rich extension property, but something much more complex. So I can read it for you. It says every K over C set of vertices has many common neighbors. And for every W of set of vertices for which this slightly smaller set has enough common neighbors in W, there exists a smallish set S, such that every set that doesn't have many common neighbors in W intersects S in these many places. Okay, no hope that you will understand. Not even I understand very well what this is saying. Okay.
So is the upper bound for K-1 overgraphs also true for ranking? Like is the proof for ranking? Okay.
That's already like that. Yes. Thank you. So this doesn't apply here. So the sanity check doesn't apply means we need to use something else than the rich extension property because and this actually doesn't hold for the K-1 graph for the sanity check. All right, so but the question stays open for general resolution. So here are the lessons we learned from clique. So resolution complexity brings a new perspective into an interpolant of between clique number and chromatic number. And it raises questions of the type, well, we have an SDP interpolant. This is the semi-definite programming interpolant, the Lovász theta. But this suggests that maybe there could be another kind of interpolant based on linear programming, because the pigeonhole principle is easy for some of monomials proofs and in terms of size. So could there be that we can replace LP size, linear programming size, the size of a linear program that interpolates in place of SDP? That would be quite interesting because SDP looks to be very, very geometric, while linear programming is a lot more combinatorial. So questions that are raised by this research. Now we have a new convoluted density property of a random graph, and it's open to simplify it. Can we connect it to more standard connectivity properties of the graph, like expander style property? Does it hide a new concept that we need to discover, like the expander were discovered back in the 80s? And for example, we don't understand very well this property, so much so that we cannot produce explicit graphs that have the property. We don't know how to do that. While today we know how to produce expander graphs, we don't know how to produce graphs that have this strange property. Now, still open, in fact, it's not even clear to find worst case instances. We don't know of worst case instances for general resolution, and it's not even clear whether the clique density, that convoluted property, suffices already. These are the lessons, and this is a work that we continued.
So for the last thing, there are reductions assuming, say, ETH, the clique requires this much time, right? So is there a way to plug through those reductions to get something?
Excellent point. I've tried this and I haven't seen how to do the reduction formalizable at resolution. That's what you would need to do. You start with hard instance for, in fact, the hard instance is counting the solutions with the most K ones. You won't satisfy all instances of that. It's hard. I don't know how to do reductions in the parameterized complexity setting. This is the question that you asked. Maybe it's doable. I'm not saying maybe I'm not smart enough to do it, but I've tried. All right, so let me now get to the coloring problem. And the coloring problem is kind of dual, right? You have a graph, you have an integer q. You want to know whether you can partition the vertices into q classes without monochromatic edges, so without edges inside the class. Classes are the colors. By the way, if you come from a more practical side and coloring you don't recognize, well, this is kind of like a clustering problem. You have a problem, you want to divide it. You know, the graph can be divided into q clusters so that every cluster is independent, right? It doesn't have conflicts. You want to minimize the number of. You can model many clustering problems this way. So computational complexity is again very well studied. It's quite important that approximating the chromatic number is a major open problem, whether it can be done efficiently, which connects to BCP theorem and unique games conjecture and many things that are going on today. And it also appears to be hard on average, but in a different sense. So that's actually what I want to talk about. Here's the encoding. It looks very similar, but it's not the same. Vertex U is colored I. You say that every vertex, fixed vertex U has one of Q colors, but every edge 4 bits I mean, you cannot have the same color on both endpoints. But the resolution complexity was studied a lot back in 2005, Bean, Culberson, Mitchell, and Moore, where they showed, so they asked the question, what is the worst case, average case resolution complexity of the coloring formulas? And again, their motivation was that the time that the resolution proof system seems to be able to simulate many backtracking algorithms. Let me give you one backtracking algorithm that I find beautiful for coloring, and this is the McDiarmid calculus. So it's a calculus where you derive non-Q colorable graphs, and you want to show that your graph is not Q colorable, so you derive it by this procedure. Here's what you do. You start with axioms saying the complete graphs with Q plus 1 vertices are certainly not Q colorable. These are your axioms. And then you have two inference rules. If you have already derived G as not Q colorable, and H is a super graph of G, and of course H is not Q colorable, so you can derive it. It's kind of a weakening rule. The more interesting rule is this splitting rule or inference rule that says that if you have a non-edge in graph H, and you have shown that H plus this, an edge between these two vertices, is not Q colorable, and the graph where these two vertices have been identified is also not Q colorable, then H itself is not Q colorable. So again, this graph is the one you obtain by adding an edge between U and V, and this one is the one you get by contracting the edge. Now, why is this sound? Well, because if the graph is Q colorable, then the two colors of U and V are either equal or different. If they are different, then this one is also Q colorable. And if they are equal, then this one is also Q colorable. So that's why it's sound. So this beautiful calculus happens to be complete. You can derive all Q colorable graphs, non-Q colorable graphs this way. And the size of the proof is defined as the number of inference steps. And now these analyses, they were interested in the connection with the resolution. If the non-Q colorability of a graph can be established by the tree-like McDiarmid proof, tree-like means that you derive graphs in a tree-like fashion, or rather like this, until you get your graph at the end, then the standard encoding is refutable in small width. This width is logarithmic in the size, and you should think of Q as a constant, like 3 coloring you're looking at, or 5 coloring. So this is constant times a logarithmic of the size. So that's a small width reduction. So you go from tree-like McDiarmid proofs to small width refutations. So the consequence is that if you prove a width lower bound for the coloring formulas, then you get a lower bound and you understand the McDiarmid calculus. And they go ahead and they prove this. You take a random graph with a constant number of linear number of edges, which is what you get on average. Then the resolution complexity has with high probability linear width and therefore exponential size. But not immediate, but it also follows. And the point is that this theorem, you prove it once for resolution, and then you apply it to many backtracking algorithms with whatever heuristics they use. Now, if we go beyond resolution, what can we say? Well, this has also been studied. In particular, the theta function of random graphs has been studied. In fact, if you take a density number of edges that is linear in n, but with a factor of q squared times n, basically, number of edges on average, then the chromatic number, the theta function gives you a certificate of non-Q colorability. Remember, if this is bigger than Q, then the chromatic number is also bigger than Q. Therefore, you get a certificate of non-colorability. And by the result of Kleinberg and others, we saw that this gives therefore a degree 2, so the sum of squares refutation of the standard encoding. And this happens at average degree Q squared and beyond. So what is the nature of these certificates? Can we say something about them? So here's the status and for random colorability and how it compares to random 3-set. So there is a threshold where after this average degree, which is the average degree, after this average degree, the formulas are not Q colorable. And this is very close to this 2Q log Q, in fact, minus log Q. Then there is another threshold where that's a threshold for the theta function, which would be C complement. G complement, sorry. This was analyzed in this Kleinberg paper. So chromatic number after this is going to be bigger than Q. After this you can certify the chromatic number bigger than Q by the theta function. Now, if you want to certify it by small width, then this goes already. Notice the difference. You should think of Q as a constant. Well, this is linear or sublinear, but it's a function of n. In fact, after this, you get the threshold for having a clique of size Q. And after this, it's completely trivial problem because you already have Q plus 1 vertices all connected between them. And notice here, there is a nice smooth transition on the width reaching this thing. Well, this region is the important one for me, because here we have that it's hard for width and for resolution size, but it's easy for degree through sum of squares. So this suggests that, okay, this is hard to find, but then can we make our solvers working on satisfiability be able to match this thing? So this is easy after all. It's doable. Of course, do you need to add this capability to your solver, or do you need to just come up with the right heuristics that would actually match this and turn this easy also for your solvers? For resolution, it's hard, but I mean, the heuristics will not work because they always produce resolution. But maybe some pre-processing, maybe something adding clauses that are not logical consequences, whatever. So this is what the region I'm interested in. Now, this region happens to be hard also for the theta function. Okay, so far we cannot say much. But of course, if you manage to match this, not by using semi-definite programming, then who knows whether this will go further, right? After all, there is no NP hardness reason to believe that that is hard.
I'm trying to parse this resolution with it. So what do you get for 3 coloring? That's something like up to edge, from constant edge density all the way to something like n to the 1/6 or somewhere around there. 1/3. Yeah, but then you probably want W to be at least square root n or something.
Yeah, and to the epsilon, for example, and then you get something to the whole.
So for resolution, it's like hard all the way from constant up to mildly polynomial edge density.
Yeah. Okay.
Whereas SOS can be with even like constant, but not too large.
Exactly, that's the point. So
Not too small.
SOS can do constant average degree, while resolution requires root n average degree. It's hard up to then. And in fact, it's not clear that it will be easier, but at least it's hard up to then. All right, so this is the status. And now what do I have? Maybe I skip approximate graph coloring. Yeah, I think I'm running out. It was 50 minutes talk, so let me skip this. Oh, okay, so let's finish with this challenge. And in fact,
you have like do well till half past. So
shall I go till half past? Okay.
We're asking questions during the talk. So
Okay, thank you. I love this. I hope you find it interesting. At least you will find it interesting. Approximate graph coloring, it's an important problem. So now we have two integers, p and q, number of scholars, and q is more than p. Now you're given a p-colorable graph. Of course, you're not given the p-coloring. You're only told that the graph is p-colorable. You're required to find a q coloring. Q can be much larger. So this is the search version of the problem. It's an easier in principle problem, right? You're given p-colorable graph. Q could be 10 times p. That's all you need to produce. 10 times p coloring. This is a search version. As a decision version, you put it as a promise problem where you want to distinguish between graphs that are p-colorable or graphs that are not even q-colorable. So there's this gap. You promise that the graph has one of these conditions. It's either few colors suffice or many colors are needed. So which one is the case? So that's your decision version of the problem. This problem is very well studied, but not so well understood. For example, the 3 versus 3 colorabilities, of course, it's just 3 colorability, it's NP complete, but already showing that 3 versus 4 colorability is hard. required the PCP theorem. It's quite difficult. It took many years, and it took many years to improve to the next one, from 3 versus 4 to 3 versus 5. It's still NP complete, but not only requires the PCP theorem, it also requires universal algebra techniques that are not easy. This is the kind of techniques that we're using the constant satisfaction problem dichotomy theorem. Now it turns out that it's open whether 3 versus 6 is NP complete. It can be shown NP complete assuming certain conjecture, like related to the unique games conjecture. It's called the D21 conjecture. There's no clear consensus whether this conjecture is going to be true, but at least we have some way to argue that, or disproving this is going to, if we do this, then we can do that. Now, it turns out that the best upper bound, I mean, this is the first that was found in 1983, but the best one is not much better than this. So you can distinguish 3 colorable graphs from graphs that are not even colorable with the square root of the number of vertices as colors. And this has been improved. The exponent here has been improved down to something like 1.5. In fact, slightly less than 1.5. So 1/5 is not the right constant. But that's all. I mean, we don't know 3 versus a constant arbitrarily large. We don't know whether it's hard. It could be polynomial time solvable. Let me explain Wigderson's algorithm from the perspective of proof complexity, because in fact, maybe proof complexity has something to say about it. So basically, Wigderson's algorithm goes as follows. It argues that if the graph is 3 colorable, if the graph, if the graph is 3 colorable, then it finds a coloring with these many colors. So now what we're going to say is that if a graph is not refutable in width 3, that's much weaker than being 3 colorable. If the 3 colorability is not refutable in width 3, then you can color it this way. And so here's the argument for it. It's quite similar to Wigderson's. So we want to argue that if the 3 colorability is not refutable in width 3, then we can color it with square root number of colors. And it goes by cases. So either every vertex has low degree, and low means less than square root of n, then it's already root n colorable by greedily coloring, because you have more colors than the degree, so you can do greedily color the thing. You always have an available color for the next vertex. So let's focus on the case that you have a vertex of large degree. Well, then what's the claim? Well, the point is that it will be enough to 3 color the neighborhood. If we manage to 3 color the neighborhood, then we can remove this neighborhood and recurse using 3 additional colors. And each time we use 3 new colors, the point is that we will repeat this at most how many times? Well, square root of n times. And at the end, so each time we use 3 colors times square root of n times. So that's 3 times square root of n. And at the base case, we use square root of n. Total, we use constant times square root of n. So it suffices then to show that the neighborhood is 3 colorable. Why is the neighborhood 3 colorable? Well, if it were not 3 colorable, then the neighborhood alone without the center would not be 2 colorable, because we would color the neighborhood and then put 1 more color in the middle. Now, if the neighborhood is not 2 colorable, then the coloring formula with 2 colors is refutable in width 2. And that's because it's a 2-SAT formula, and 2-SAT has width 2 refutations. But then from this formula to this formula, there is this change, but in fact, we're only adding 1 vertex. So basically, we're only adding 1 closed, and therefore the width goes from 2 to 3. And therefore, we have that this is refutable in width 3. But if a subgraph of the original graph is refutable in width 3, then the original one is also refutable in width 3. So that's the argument, and that's all there is. And what this is pointing out is that this case analysis, in one of the cases, you don't need to assume 3 colorability. It's enough to assume consistency with respect to 3 colorability. Then we ask how much further can we do this? And well, we didn't manage to get to n to the epsilon, which would be quite nice, because remember, 1/5 is the best that is known in polynomial time. But we were able to do that in some non-trivial sub-exponential time. So the width is sublinear. And the corollary is this, is that we can do the 3 versus n to the epsilon coloring problem in some sub-exponential time. And notice, I mean, this doesn't look very good, but at least it's not strongly exponential in the sense that this epsilon on top of it is at the exponent of the exponent, right? So this improvement here is noticeable. There is a naive algorithm of 1 minus epsilon. We achieve this factor of 2. This is the important one. And this is based in case analysis, as in Wigderson, is a bit more complicated. So in the distinguishing case is whether some set has large neighborhood or not. And then you, in one case, you loop over colorings, and in the other, you can do something. This one is actually independent cases, and this is where we use the 2 colorability assumption. Now, in this case, instead of being 2 colorable, what you get is an instance that is 2 least coloring. What does it mean? It means that every vertex has only 2 available colors, but they don't have to be the same all the time. And 2 least coloring is still refutable in with 2, and that's why it works. Okay, so if you want to look at the details, they are all here in this slide. I'll pass the slides. All right, so let me now wrap up and finish. So half past as I've been given. So here is a challenge. So as I said, I want to find the hard instances to make progress on improving the algorithms. That's the point. If we don't know what is hard for an algorithm, how are we going to improve the algorithm? We can try it, but we want to know what is that makes it hard, and to focus on that, for example, and to be able to compare. And that's why I focus on this region as an example. So this region says that it's easy for degree to SOS, but it's hard for width. So the point would be to match this without using semi-definite programming. And I've given some evidence that this is kind of maybe possible. For example, in the clique case, we already gave this evidence that there is a pigeonhole instance somewhere there. And okay, that you can do with SOS, but you can also do without, because after all, pigeonhole we already know. If we find the pigeonhole, we know it's unsatisfied. So this is a possibility that is try to do the easy cases that now exist, easy for another algorithm with an improved resolution. Resolution itself won't do it. So the challenge then is to do, well, you can do these experiments, and I've had a student, Kilian Rothman, doing these experiments back in Barcelona. So you can feed your algorithm with either a random graph at the right large density, at the right density. And in fact, we can make this explicit because this, the thresholds for the theta function are very well understood. So this 18, in fact, it's over generous. This should be 15. So for 3 coloring, average degree 15, okay, and large. We didn't try 2 large ends. You feed a random graph or a random graph with a planted Q coloring. You feed this to the algorithm, and the algorithm should be able to distinguish one from the other. You put the timeout. That's the point. And so, but of course, the current SAT solvers, I mean, the ends that we tried, they completely solve the thing. So we need to try much larger ends, and then it should be difficult according to the theory, it should be difficult set of instances. And then the challenge is to improve the solver to actually give the right statistics distinguishing one from the other. Okay, so I'll leave it here, and I'll thank you for your attention.
One or two questions before the break.
If anybody's, you're using Erdős-Rényi random graphs. Have people looked at quasi-random graphs? Ron Graham and Fan Chung have this theory of quasi-random. In other words, you say that it has certain statistics.
Yeah, it has the right number of C4s and this sort of thing. Yeah, that's a very good question. This is attempted by this. I trying to identify the properties that the graph has, like having this rich extension property. This is along along the lines of quasi-randomness. But the specific question about whether quasi-random graphs in the sense of Graham and others has been done, the answer is no. So it's a good question.
But, you know, there's room for theory for that kind.
But there's room for theory.
Special about 3 in the approximate graph color. Like, does it work for 4? Like, you can't make the same kind of consistency argument for 4.
Yeah. No, because the point is that two sets is special, 2 sets is solvable with 2. While 3, no, you reduce from 4 to 3, but then 3 is that hard.
So already you're into like PCP land. That's kind of the point, right? Because you said
It's already yeah, the PCP
Yeah.
thing, we already don't know what 3 versus 6 is.
So let's thank Albert again.